Started with Jonathan Luke, who will speak about weak null singularities from vacuum.
Thank you very much. Let me start by thanking the organizers for having me here. It's actually my second week in this program, and I have been really having a great time, both sort of enjoying the city and the talks. So today I'm going to tell you something about weak null singularities. So I want to somehow mirror the title of the conference that you guys set, which is from vacuum to matter. Okay, so because of that, I should start with vacuum. So let me start with the Einstein's equation. Right, so the intention is at some point I'll talk about matter, but at the moment there's no t. Right, so let's start with t equals 0. Okay, and let me actually, even before talking about weak null singularities, let me start by sort of recalling a different kind of singularity from yesterday, and we see Warren just walked in. So the first kind of singularity you can write down, right, are space-like ones, which in particular Warren told us about yesterday. So let me look at a slightly different setting, not Kastner, but Schwarzschild, because I was thinking about black hole. And in Schwarzschild, as we know, there is a space-like singularity in the interior of the black hole, right? So this is a singularity, it's space-like here. And the singularity is, as I just said, a space-like. And it's, in some sense, you should think this is like what we thought about yesterday, right? So this is Kastner-like. In fact, locally, it really looks like Kastner. And in fact, it's sort of a very bad singularity. You can think of it as a crushing singularity. And in particular, as shown by Spearsky, this is a C0 inextendable. So if you remember from Warren's talk yesterday, right, so there was a certain proposal that this kind of singularity is generic. Okay, so what I'm going to talk about is a different kind of singularity, sort of in contrast. So I want to look at a different example of vacuum solution, and this is the Kerr solution. So I want to talk about the Kerr solution. Of course, you tell me that Schwarzschild is an example of Kerr. So let me look at the Kerr in the range where the rotation is in this range. Okay, so it's strictly rotating, but it's a sub-extreme mode. And in this case, the Penrose diagram, of course, looks very different, and it again has some black hole region as before. But if you look at the maximal globally hyperbolic development of initial data, there's no singularity whatsoever. Okay, so you have a Cauchy horizon here. So this is the Cauchy horizon, and everything is smooth. So no singularity. So this is a smooth Cauchy horizon. Okay, and this is despite the fact that this is a geodesically incomplete spacetime. So despite, if you look, despite being geodesically incomplete. Okay. So if you are geodesic brave enough to go inside, you will still end at some point, right? So at the Cauchy horizon. However, as you get to the boundary of the spacetime, there are no singularities whatsoever. Okay. So now, if you were to believe somehow when you have geodesic incompleteness, you should have something of a singularity of this sort, right? Then you may expect that this is non-generic, and maybe if you perturb, you get something like that. Okay. So here's the question, sort of, one would like to ask is what happens if you perturb? Okay. What happens? Oops. Happens when we perturb 2? Right, so the Kerr case. Okay, so everything's still within vacuum. I want to look at data, and I want to perturb data, and I want to ask what happens. Okay, so here's sort of the expectation. So the expectation is the following. So the expectation is if you look just in the exterior of the space-time, so let's say if you just look in this region, Okay. Oh. So in the exterior, if you perturb, two things will happen. The first thing that you expect to happen is that, well, this is stable. Okay, you perturb, everything settles back down to Kerr. So it settles down to Kerr. In fact, it's a bit better than just what you expect. In fact, this is proven, at least in some cases. So not just only an expectation, but in fact, it's proven. Well, if you include the exterior, sort of they don't really look so different. So let's think about them sort of simultaneously. So the exterior is stable, and in the it's known in the A equals 0 case, and in the case where A not everything, but when A is extremely small, let's say much smaller than M. So these are works by Lafermas, Hosego, Rodnyansky, Taylor, and Georgi, Kleinman, Cheptel, Shep. Okay, so this is around early this decade. Okay, so that's the first expectation, is that okay, everything in the exterior is stable. Now there's another expectation in the exterior, which, okay, so this is also expected somehow for the full range, but that's not known yet. Okay, but there's another expectation, which is in fact one not only just goes out, settles down to Kerr, but it settles down to Kerr with a precise asymptotics. So generically, right, settles with precise asymptotics. Okay. So this is really in the fully nonlinear case. If you want to think about the vacuum-Einstein's equation, this is really not known, but this is expectation. But what we know is that we have over the years sort of better and better expectations. So the first work sort of thinking about these kind of issues. It's a work of Price already in the 70s. Okay, so this is not a proof of, certainly not in the nonlinear case. What sort of Price suggested is that now, if you think everything was settled down to Kerr, now let's think of some particular curvature component. Okay, and this is the curvature component that will satisfy a decoupled equation, which is called the Tukhowsky equation, and let me from now on call that component alpha. Okay, so that's if you want to think this is a particular curvature component. And Price suggested that if you perturb Kerr, and when it settles down to Kerr, there should be a precise asymptotics if you think, let's say, Eddington-Finkelstein type coordinate u bar. You should expect a decay rate of u bar to the -7. So not only does it go to Kerr, but generically it settles down in a very, very precise way. You can even be more precise to say what this profile you expect to look like. More recently, so there are suggestions. So Kerr-Berger first, sorry, 21. And then there are other works, Geisch, Kerr-Berger, let me not spell, Kerr-Berger, Massoud. These are 24, both are here. Who suggested that, well, in fact, you should really think about this problem by thinking about sort of more physical situation, by thinking about things from past null infinity. If you think about that problem, naturally, you will have some non-smoothness at future null infinity, and actually that determines the rate. Okay, so what they suggest is that rate determines by failure of peeling, and you expect something much lower, which is only -4. Okay, but again, you expect something sort of precise that it will settle down generically. If you think about this more general class, this is what happens. And there's some work I did with Sungjin Oh, which suggests that actually even if you have smooth fusion null infinity, even in peeling, even with peeling, actually one expect nonlinear effects to come into play, and you expect something also slower than price. Okay. So I'll not say anything more about sort of these exterior expectations. If you're interested, stay for next week. Okay. But now I know what to expect in the exterior. And then now I want to ask what happens in the interior, right? In particular, what's going to happen with this lack of singularity? Is it true that I create a singularity? So this is the first theorem I would like to talk about. So the theorem has two parts. Okay? So the first part of the theorem, let's call it A. So this is joint work with Mihalis Dafermis a while ago. In fact, if I remember correctly, last time I was at Field, I was talking about this. So feels like I'm still talking about the same thing. Anyways, so the result is if one is true, okay, and it is now unconditionally true in some cases. Okay, so maybe I should emphasize this, right? This is expect, right? So this two I don't know, but one there's some case I know. Okay, so if one is true, then I know at least that things are not going to revert to that case. Okay, so then the solution has a Cauchy horizon near time like infinity. So in particular, the picture would at least look like this. Okay, so there's a piece that looks like this, but there's a CH plus. However, things are now consistent with having singularities. Okay, I'm just saying that the picture looks like this, and I'm saying, moreover, that the metric extends. Metric extends continuously to CH plus. Okay? So at the very least, I have a metric. Everything is nice in the sense of continuous things, but it's still consistent with higher norms going up. So that's the result 9 years ago. And then I'd like to present our new result. The new result is joined with Spieski. And there's also a very nice independent proof of the result by Gurieren, which appeared around the same time. The exact statements of the theorem are slightly different, but okay, at the level that I'm going to discuss, they will look the same. And the theorem says the following. So now assume 2 holds. Okay, so if 2 holds, and it doesn't really matter what you assume. Okay, so if you want, you can assume this. If you want, you can assume this. If you want, you can assume this. Okay? Doesn't matter. Any of these hold. Then, in fact, there is actually a genuine singularity here. Okay, so then the space-time metric cannot be extended beyond the Cauchy horizon as a Lipschitz metric. Okay, so we know that everything extends continuously, but that's sort of it. Okay, modulo. Okay, there's some okay the gap in between C0 and C1. Okay, but if you want to think in C1 or C01, you can't extend. Okay, so there's some singularity, as long as you assume sort of some lower bound of alpha along. Okay, this is maybe along the event horizon. Okay? So as long as you assume that, then you have something that you cannot extend in Lipschitz class. And conjecturally, generically, you have some lower bounds. Yeah. So that completes the picture. So in particular, modulo having to prove things sort of in the exterior, right? What it says is that the picture is very different from here. In fact, it's also very different from here, right? It's a picture where you still have a Cauchy horizon, but generically you have a singularity. Yeah. So this kind of singularity is what I would like to call weak null singularities. Okay, and what do the singularities look like? Okay. So I already give you some features, right? It has to be C0 extendable and Lipschitz inextendable. Okay, but in fact, one can have a rather precise description of it. Suppose I look just locally near the singularity. Okay, so what it looks like is that you can choose double null coordinates. Double is not so important, but null is sort of important because I want coordinate which somehow it's parallel to the eventual singularity. Okay, so okay, I might as well think double null. That's my coordinate system. So this is U and U bar. U bar and U. Okay. And if I look at regular coordinates, so let's say I look at regular coordinates. So not the coordinates I think about above, which is normalized in the exterior. I think about local regular coordinates here. It looks like the following. So metric is, let's say, so it looks like the following. Gamma AB. So this is just the form of the metric that I choose. This is just double nullness. But it has the feature that you should think everything is continuous up to the boundary. So all these things are continuous. B, continuous up to boundary. Up to boundary, let me call this U bar equal to 0. Up to U bar 0. But it's a bit better than that. That everything is regular if you are tangential. So you can differentiate as many times as you wish tangentially to the boundary. Okay. So if you want to write in coordinates, you can differentiate differentiable as many times as you wish. Differentiable in du and d theta as many times as you want. Okay. However, something bad happens in the u bar direction, which is exactly why things are not Lipschitz extendable. And you should think the u bar, du bar of gamma or du bar of log omega, these objects, you should think they are bounded above, and this is quite important, by some explicit profile that you can think about. So the profile that you would like to think about is something like 1 over absolute value of u. So this grows to infinity as you go, right? However, there's a logarithm here for some p bigger than 1, okay? And this p depends on what happens in the exterior. And in particular, this is integrable, okay? Integrable. And therefore, it's consistent with things, because you can integrate the derivative, it's consistent with things being bounded. So this is this is what I will now, from now on, call weak null singularities. Okay. So I'm lucky enough to have Jan being the next speaker. So he'll tell you about the proof of this, and I'll not say anything more. Okay. So modulo things that modulo things that Jan will tell you. Somehow this is the vacuum picture, right? So the vacuum picture is you can look at curve, you perturb, okay, and you have some expectation about the exterior. Assume all the expectation about the exterior. Then the interior, you know that there's a Cauchy horizon. The Cauchy horizon is a weak null singularity. Locally, it looks like exactly this. So now I want to go to the second part of the talk. I want to ask, okay, given we know this in vacuum, what do we know when we add matter? Okay. So That's matter. So there's equally two questions here, right? So one question is, if I couple with matter, what happens to the matter? Okay. Now the second question is, if I couple to the matter is a self-gravitating, so it will affect the geometry. And so I would like to ask, if I do that, is the sort of structure of the singularity going to be the same? Will I destroy this? Okay, so that's two questions I want to ask. Now, some of you in the audience may say, wait a second, don't you already know what happens with matter? This is because before sort of all these things were studied in vacuum, they were first studied in spherical symmetry, like many of the problems. It's much simpler there. And then necessarily one has to think about matter. So there are some cases where we already know with matter that we know something about this singularities. Okay? Indeed, that's the case. And let me just recall some of the results there. So the thing that we know in those cases, for instance, it has to do with scalar field matter. Yeah? So this is just usual this and the corresponding T that we have seen multiple times yesterday. Okay. So let me just state a theorem. So these are things we know in spherical symmetry. Okay. So let me combine a bunch of works. So if you combine the work of the Fermat-Raniansky, and my work with Sung Jin. So this was 03. This is I think 17. Okay. Then for the Einstein-Maxwell scalar field system in spherical symmetry, Einstein-Maxwell scalar field system in spherical symmetry, we have a rather complete picture. In particular, not only do we know A and B, the analog of A and B, we also know the analog of 1 and 2. Right? So we really know sort of everything. And in that case, what we know is that, in fact, we know that generic data, and let me emphasize, really, I'm talking about generic, no smallness even necessary. So generic data would give rise to a space-time with a weak null singularity, exactly of this type. Okay, give rise to a solution with weak null singularity. Let me just call it like this now. This is called weak null singularity. Okay, exactly at this form of the metric. Okay, but then because now I have matter, I can also say something about matter. Okay, moreover, if I again look in this type of coordinate system, which is regular at the singularity, I know matter field has the following property: phi remains bounded, but du bar phi goes to infinity towards the singularity. Okay. And moreover, now if you compute, right, this would tell you that if you look at Ricci, which you should think as sort of seeing the matter content of your space-time, will also go to infinity. Okay. So this we know with matter field. I should say there's also very nice work sort of giving an even more complete picture of this spherical symmetry model, recently completed by Onyx, but I don't want to take away her punchline, so I'll let her tell you about the result in the afternoon. Okay. So this is nice, right? You say something about matter. Okay. Now you may complain that, well, this is just spherical symmetry, but it turns out that this phenomenon is actually very robust. Okay. So if you look at so if you sort of use what I did a while back, what you can say is that somehow this phenomenon, this behavior of the matter field is stable under non-spherically symmetric perturbation. So stable under non-spherically symmetric perturbation. So what's the setup? So the setup is you look at one of these things there, let's say. Okay. So then you know you have a strictly symmetric thing. You know everything, right? So in particular, you know everything, and you know here it's a weak null singularity. So what you can do is, okay, let's look locally, and let's just look at somehow locally here, and now introduce more non-strictly symmetric perturbations, small but non-strictly symmetric perturbation. Right? And you know that everything persists. So there exists a solution here, and everything looks like what they're supposed to. The metric part looks like that. The scalar field part looks like that. Okay. Let me lie a little bit. Sort of what you almost want to say is the following. You want to say, okay, you understand this, right? Solving Einstein's equation, which is the system of wave equations. Okay. Now you add another wave equation to it. Okay, what's going to be changed, right? It should be the same. Okay, that's essentially, okay, not quite, but that's essentially why this is true. Okay. So this sort of tells you with scalar field matter what's going to happen. Now I want to think about more realistic matter. Okay. So the next thing I want to think about is Euler. So I want to think about Euler, and I want to ask what's going to happen. Yeah. Now let's quickly write what that is. So I want to think this is the Euler stress energy moment tensor, and I want to say this is a P plus rho. Okay, so let me introduce the objects. So this is the pressure of the gas. This is the density of the gas. And then V mu. And this is the velocity of the gas. And then this is P, again, the pressure, G is just the metric. Okay? So I want to think about this. So there's the equation of motion just given by the divergence has to be 0. That gives you the Euler equations. And I want to, well, eventually I want to couple with Einstein. And I have to set that G of VV has to be -1. Okay, so this is how the time likeness of the fluid velocity. And if you look at this, the system is not closed. So I have to introduce the equation of state. So I have to set P as a function of rho. And in fact, I'll set it to be some constant multiplied by rho. Okay, and this constant is the speed of sound. Okay, so CS is the speed of sound. And for reasons that the speed of sound should be less than the speed of light, I will set it to be less than 1. Okay, so I'll think about it in this range. So what I now want to ask is, okay, suppose now I couple Einstein with Euler, and then try to understand sort of this regime. What am I going to see? Yeah. Now, again, maybe you're going to complain. You will say, well, don't you already know that? Well, because of the following. Because it is well known that if you look at the particular case, which is CS equal to 1, okay, so the speed of sound equals to the speed of light. And if you look at irrotational fluid, let me not say exactly what that means, but there's sort of some suitably defined notion of vorticity being 0. Okay, then the equation actually it's well known. This is okay. So this is called the stiff fluid case. And this is well known that the equation reduces to the scalar wave equation, okay, scalar field equation. So we reduce to something. No. So this is get the scalar field equation. So then we know how scalar field is going to behave. Okay, quite true. And let's write that down. And in fact, you can now try to use this correspondence and try to interpret this result in the fluid world, right? Because okay, I have some scalar field, but the scalar field should correspond to some fluid quantity. I want to understand what happens, what happens, sort of about this. How does it correspond to fluid? Okay. So this has recently been done in the work of Manscheffer, student of Jan Zbierski. So what she showed is the following. So if you look exactly at this setting, okay, so if you look at irrotational, in fact, also strictly symmetric, irrotational, strictly symmetric stiff fluid. So the setup, okay, it's not so important, but the setup is uncoupled on the weak null singularity background. Okay, it has to be strictly symmetric so that everything makes sense. So for instance, you can take one of these, right? So in particular, you can think of this now as a stiff fluid. So what's going to happen? Like there's some blow up, and I now want to interpret the blow up in fluid variables. So what's going to happen is that then, if you think about the density of the fluid, it's going to infinity as you go towards the weak null singularity, and moreover, the velocity becomes null. Remember, I have to set that the velocity has null minus 1. So the picture you should have in mind is that you would have your velocity, right, which has to be time-like, right? But as you approach the singularity, it becomes like really stretched. So this is a sort of blow up of the becomes null. Okay? In particular, it's also the case, right? You can think here, it's of course also the case that Ricci goes to infinity towards the weak null singularity. Okay, so this is you should think this is like scalar field, but interpreted in the fluid world. Okay, but now you can ask the following question. Okay, this is very special. This is this particular case where I can just use things I understand. What about the other cases? Yeah, and it turns out that already in the simplest case you can think about, you will see something different. And another simple case that one can do other than the stiff fluid case is exactly the other extreme, which is the dust case, which is C when CS equal to 0. So in this case, things are slightly simpler because it's sort of decoupled. You can first solve for the velocity and then solve for the density. Okay. But long story short, what Manscheffer also showed in the same paper, okay, is that if you look at sort of instead of dust, okay, so look at the dust case, again on a weak null singularity spherically symmetric background. Okay, what you see is that thing is actually different. Okay? What you see is that then rho and v remains finite. So rho remains finite, and v remains time-like. Okay. So already you see there's a different phenomenon, and now yes. Uniformly tight, yeah. So it has it achieves a limit. It achieves the limit. It achieves the limit at the Cauchy horizon. The limit is a time vector. Okay. So this already shows that there's something different that's happening. Now you can ask, okay, more generally, what's going to happen? So this is the theorem of Yue Song. Okay, so let me say the setup. So the setup is following. So consider now I can even couple Einstein Euler, and I want to look at what happens near a weak null singularity. Okay, so importantly, I have to think about Einstein Euler, but importantly, I have to remove this case. Okay, because this case I know things blow up, so you have to set the speed of sound. It can be 0, but it cannot be 1. Okay. So now consider the characteristic initial value problem. characteristic initial value problem, where I just want to understand if I add Euler to this picture, what's going to happen? Okay. So what's the problem that I'm going to consider? I'm going to consider characteristic data. Okay. So this is a local problem, so you should think these are very short, but okay, I draw it longer so it's easier to draw. So what do I want? I want everything to be nice here, right? Because you should think here, okay, I'm away from the singularity, so this is just smooth data. And then here, for now, let me put in something. I need to put in data for both the gravity part for Einstein and for the Euler part. And let me, for now, just put some singularity in the Einstein part. Okay, so the metric behaves like this, exactly like this, right? What we understand in vacuum. Okay, behaves like as a weak null singularity. And let's, for the moment, just put Euler to be very nice. Okay, soon I'm going to change, even generalize that a bit. But let's say the gas, so fluid, is regular. Okay, and by regular I mean it's also away from vacuum. So rho is bounded, but bounded also from 0, free of vacuum. Right, so I really have some fluid. Now then I can try to study this problem, and here's the conclusion. So the conclusion is that in this full range, I can solve. I have a solution. Yes.
So that's in the transverse direction, right?
Yeah, yeah, exactly. Yeah, exactly.
It vanished.
So
Null singularity when you approach the smooth data.
So I go here.
Yeah.
Well, so all the singularity is just here, right? The singularity is exactly, all the singularities is about the derivative. Yeah.
That derivative can now be considered backwards.
Yeah, yeah. No, but it blows up, right? It blows up towards here. So anywhere away is smooth. Yeah. Exactly. So then, right, locally, let's say for epsilon small, right? What's epsilon? Epsilon is the size of the length, right? As compared to the size of the data. So for epsilon small, there's a solution in the full region. You can solve here. Everything is moved up to here, but this is a singular. So you can solve up to the whole rectangle, and you have a singularity. There's a solution in this region. In this region, right? The metric is a weak null singularity. Metric is a weak null singularity. That is to say, well, first of all, it's continuously extendable. It's not Lipschitz extendable. And moreover, it has a particular precise profile as before, right? So I can differentiate in these type of directions, and that's nice. Okay, if I go this direction, there's a particular profile that the derivative blows up. Okay. Now now what happens to the gas part? Turns out the gas part is more regular. Okay, so the fluid variables, let me write it like this. So there's a velocity, okay, and there's also rho, but let me write log rho to emphasize it cannot be 0. Okay, extends continuously. Continuously to the weak null singularity. Okay, and moreover, the Ricci curvature, which of course measures the meta content of the space-time, also extends continuously. So the Ricci curvature extends continuously. So the picture is in stark contrast with the scalar field case. Okay. On the other hand, there's no contradiction because I have removed the stiff fluid case. So I do need, as an assumption, that the speed of sound has to be strictly smaller than the speed of light. And of course, epsilon depends on CS exactly. Okay. No, sorry. Oh, this is extremely important. Sorry. Yeah, in general. So this is without symmetry. So I really want to look at the case. I'll draw a picture in a minute. That I want to think of. I already have these vacuum things that we understand. Now stored in some fluid. I want to understand what happens. No symmetry. Yeah, thank you. So yes. Pretty comfortable, right? Because in one you impose data. Correct. 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 Good. So you already gave my remark. But the problem is you gave my remark too. So let me first do remark 1 and I'll come back to this. So remarks. Sorry, let me get some water. Oh. So the first remark is that even if you impose the fluid to be extremely nice initially, this would not propagate. Okay, you would have to lose something. So as you propagate, you would see that in fact I told you that rho and v remains nice, but really it's just continuous. And in fact, in general, you will see that the derivative of these, they go to towards the weak null singularity. Okay? So because that's what you prove anyways, so you might as well also assume you can also consider a stronger theorem. You don't really need it to be regular. You can also allow derivative blow up in a suitable way. Okay? So this is a nice class where you can prove sort of local propagation. Spir's complaint still stands that this is just local propagation. Okay, if you assume that, then you propagate. Okay. Now, I just want to make a remark. Okay, so the derivative goes to infinity. You might think this is a rather scary thing, because as we know, just Euler. Forget about the fact that you have Einstein. Just look at Euler. If the derivative of fluid variable is large, you may form a shock, right? But nonetheless, the claim is that there's no shock here. Yet no shocks. And the point is the following. The point is, of course, we know roughly that the time you need to form a shock is inversely proportional to the size of the derivative of v. Right? So this goes to infinity is very dangerous. But it goes to infinity in such a way that if you try to compute, you actually gain logarithmically. So before you have enough time to form a shock, you run out of space-time, and therefore nothing bad happens. Okay, so that's the point. Now, the second thing is the real problem is still open. This is what Spirus is saying. And ultimately, what one really wants to do is the following question: is you want to construct a solution that looks like this. Construct a solution where you have let's say something like Kerr that we understand very well, and something converging to Kerr, let's say in the exterior. In the inside, you have a weak null singularity, and you want to consider some body of fluid going in like this, right? So eventually, this would be the problem that one wants to think about. So in particular, it's a free boundary problem that on its own, it's quite difficult. We'll hear more later in the conference. But this problem that has been solved in this picture that one finally wants to understand is really just this little bit, right? So that's now has been understood. But okay, there are more global things one have to think about. And in fact, Song was telling me that he expects, if you look at this is another color. If you look at this problem, actually you might even expect things might degenerate here. Okay, so there's something in the when the boundary hits the singularities, there's something even worse that's happening. But okay, nothing is known yet. Okay, so that's the theorem I want to tell you about. So let me tell you something about the proof. Can I go 10 minutes? Okay. All right. Anything I forget to say? Okay, good. ideas of the proof. So unfortunately, the proof also has to be from vacuum to matter. So I have to first tell you something about vacuum before one can even say this. So first, what does one have to do even for the vacuum problem? So the main issue, somehow why this is difficult, is of course things are very irregular, right? There's very low regularity. And the only thing that I can try to use is the fact that, okay, very low regularity, but it has very precise structure. And that I have to use, right? In particular, this thing that only blows up in a monotonic way towards that. Okay. So already in the vacuum case, one of the key problem is that, okay, I'm without symmetry, as Martin reminded me to put in big letters there. So therefore, I have no choice but to do energy estimates. I have to do L2 estimates. The first problem is that the curvature is not in L2. Right? So then I can't do energy estimate. It's worse than that, actually. It's actually not in L1. Okay? So that feels very bad. Okay? But then somehow all these analyses, in particular, were used in the works to understand Kerr and so on, relies on the following realization. Well, a few realizations. So the things are bad. Okay. So there are some curvature components which are bad. So let's call them bad. Okay. However, not everything is bad, right? Precisely because of the particular way that the singularity looks like. So there are components which are good. Sorry. There are some bad. Sorry. And then there are some which are good. And what do I mean by good? Good, I mean you expect it to even be infinity. Okay, so you can try to make use of that. But then there are some which are even worse, right? As I said, they are really bad. So let me call them a terrible. And these are things which are not in L1. Okay, so that's fun. Okay. And let me just say that actually there are two classes of bad things. So let me call it bad and bad tilde. Okay, so that's these are things which are not in L2, but at least they are in L1. Like okay. Now the idea is you have to construct norms which are consistent with all these behaviors. Okay. So the idea is the following. So if it's really bad, then let's just forget it. Okay. Now if it's really good, then of course I keep. I don't do anything. And for these, I play around with it a little bit. And what I want to say is I should correct it. And in fact, there's a good correction that one can introduce, which is instead of thinking about R bad, I can think about, let's say, R bad check, which is R bad plus a quadratic correction involving connection coefficients. Okay. And it turns out that if you look at these things, there's sort of a surprising miracle that even after you forget this, these things form a closed hyperbolic system. You can just estimate that without doing this. Okay, so this form closed hyperbolic system. And now you can try to construct norms which are consistent with all these behaviors. Okay. So what would be the norm that you would like to use? The norm that you would like to use is terrible is alpha. Yeah.
What's an example of an object?
What's an example? Okay, fine. This is alpha bar. This is beta bar. This is the rho sigma. This is beta. This is alpha. Okay.
So like beta plus beta times pi.
Say that again.
Like beta plus half beta.
No, I correct rho and sigma.
What's beta? Is beta?
Beta is the tilde. Tilde I just keep, but it's still bad.
Okay.
Yeah.
So rho minus half.
Exactly. Yeah. Okay. If those sounds Greek to you, don't worry about it. Okay. So what do I want to do? Now what I want to do is I want to control energy estimates. I want to really think right. So remember, this is where these should be worse, right? Because you have to think things with this is where the singularity singularity is, right? So this is the direction. And then I want to think about energies in these, okay? So the good things are fine. The good things are fine, okay? But the issue is if you have to control the bad things, you necessarily have to put in some weights, which degenerates as you go towards here. Okay, so it's important that you stick in a weight which degenerates. Okay, and because you put in a weight, this is a system, right? You put in a weight or something, then okay, it also appears on something else, and you will see this. You will see this here, and something like this. Okay, and then you want to show this is bounded data plus error. Okay, so that's sort of roughly what the norm you want to say. Of course, you can create whatever norm you want, but there are two things that has to be satisfied, right? One is that you have to satisfy linear estimates, right? You have to you introduce weight, you introduce bulk terms. The bulk terms has a good sign, and that it's okay. So it turns out this is okay. So the first thing is that you have good linear estimates always. And of course, the second thing is that you worry that you control something extremely weak, right? You control something extremely weak, so the error term better corroborate, right? Which is consistent has to be with this extremely weak thing, and it does. And this is the null structure in the null structure in the equations, right? And this is I just tell you what to do with curvature, and it turns out that you can actually differentiate because everything is adapted to the null double null coordinate. You can just differentiate in the angular differentiation, and it keeps the structure. Keeps the structure. Okay, so this is sort of vacuum story in the nutshell. Now I have 4 more minutes to tell you a little bit about the Euler story. So the thing I have to understand, of course, is what kind of energy estimate I can prove. And here's the key here. So Euler. So one of the keys is the following. So the key is that the speed is less than 1, right? I have to use this, otherwise the theorem has to be false. Okay? So since CS less than 1, this implies if I look at these hypersurface, incoming null hypersurface for metric, okay, they are actually space-like for from the point of view of Euler. Because Euler travels slower, so these are space-like. Okay? So in particular, unlike in the Einstein case, where okay, you have to think about different components of curvature differently because you are thinking about null hypersurfaces, these are just space-like hypersurfaces for Euler, and therefore energy estimates control everything. Okay? So therefore, you can expect you can have an estimate which is log rho v, let's say, squared. Okay, you can control this. Okay, this already suggests. I mean, if one is naive, this already suggests it satisfies estimate that's like R good. So this should be as good as R good. Okay, so this is similar estimate, similar as R good. Okay, there's sort of one technical thing that one has to think about, which always is the thing that is annoying in this type of problems, which is you introduce double null coordinates, which is naturally adapted so that everything is nice for the Einstein part, okay? But it's not so naturally adapted for Euler, okay? So in order to commute, so first of all, you cannot just commute with angular, okay? The equation does not, this is double null for Einstein. The equation of Euler does not allow you to do that. So you have to commute with more things. So in particular, you have to commute also with the other regular direction. But more importantly, you have to decompose your velocity field in a way that respects the double null structure. Okay, so after suitable decomposition of E. And the point is, if you don't do that, you may lose derivatives. Okay, to avoid loss of derivatives. This is because you don't, in the double null coordinate, you don't control all crossover symbols at the same level. Okay, so you have to avoid that. Now, of course, you'd say, well, still, okay, you don't control every derivative, right? You can only commute with that. You don't want to commute with u bar because u bar is bad because you have a singularity. Okay. Now, how do you control u bar? So the final thing you notice is that the u bar derivative, so control u bar derivative using the equation. Using equation. Again, this is because this is space-like, right? This is space-like and in particular non-characteristic. And therefore, the equation should let you control the derivative, which is transversal. Okay. And now the point is that you use the equation. The point is that when you use the equation, you are sourced by something that you see from the Einstein-Patrusius singular. Sourced by the metric part, which is singular. But fortunately, it's singular in a very specific way with the profile if you remember, which is looked like this. Okay. And in particular, this is in L1. And this is the only source of reason that this is singular. Okay. And therefore, you can show that the U bar derivative is in L1. And it turns out this is exactly what you need to rule out possible shock formation. Okay. All right. Sorry for going over even with the extra 5 minutes. Let me finish here.